Hello, my name is Tomoki and I am a postdoc at the University of Basel in a group with Professor Daniel Ross. Today, I'd like to talk about Magnonic topological insulator in antiskyrmion crystals. So this work was done when I was still at the University of Tokyo, and the details can be found in this reference. So magnons are countable spin waves in magnetic systems. Since they can carry spin current in magnetic insulators and they are free from Joule heating, they are considered as a future candidates for information carriers in the field of spintronics. One of the possible routes towards Magnon spintronics is to use the concept of the band topology in Magnon band structures. Following the bulk boundary correspondence, the non-trivial Magnon band topology stabilizes the edge-localized Magnon modes that can propagate in a chiral fashion. And since these chiromagnonic edge states are robust against weak perturbation, it suggests the possibility of unidirectional robust Magnonic spin currents along the sample edges. So far, there have been many theoretical proposals on these topological magnons, including X Magnonic crystals and pyrocoel lattice, and many more models to follow. And recently, a new topological phase called higher order topological insulator was proposed, which supports boundary localized state with spatial dimensions lower than 2 or greater than 2 compared to the original spatial dimension. So here I'd like to introduce it for magnons in a two-dimensional systems. The conventional topological phase of magnon is classified as Chan insulators since the time reversal symmetry is broken. And in these systems, the topological invariant is a Chan number, and we obtain the Magnonic chiral edge state from the bulk boundary correspondence. So this supports one-dimensional boundary localized state. In contrast, the second order topological insulator is characterized by a Magnon quadrupole moment of magnons, and it supports a Magnonic corner state. So this is a zero-dimensional boundary localized states. And in this work, I'd like to talk about this new topological phase of magnons. And we should note that for the second order topological insulating phase, we need a spatial symmetry such as mirror reflections and rotational symmetry. And one of the difficulties to realize higher order topological phases in magnetic systems is that the magnetization along the sample boundaries must be also compatible with the symmetries that protect the higher order topological phase. So if the symmetries is broken at the sample boundary, we no longer have the bulk boundary correspondence to stabilize Magnonic corner states. And unfortunately, it is quite easy for the magnetization along the edges of the sample to get deformed in magnetic systems. For example, the Jaroszewski interaction that is arising from the spin-orbit coupling leads to twisted spin textures along the sample edges in ferromagnetic systems. And furthermore, upon decreasing the magnetic field, the twisted magnetization along the sample boundaries undergoes an instability to nucleate striped domains from edges into the bulk of the sample in the ferromagnetic systems. So the spin textures in the finite sample is another important problem to realize Magnonic higher order topological phase. And interestingly, it is also possible to restore the symmetries due to the reconstruction of the magnetization along the sample boundaries, as we show in this work. So let me introduce skyrmions. Skyrmions are topological spin structures in magnetic systems, and it is so here I show this typical spin configuration of skyrmions. Which is the spins rotating from the downwards to upwards as we go away from the center. And by collecting all the spins to a unit sphere, we can see that they cover the surface area for an integer number of times. And this gives the integer quantized topological charge of skyrmions. It is also possible to have the the opposite sign of the topological charge compared to skyrmions, as shown in this antiskyrmion configuration below. And recently, these antiskyrmions were observed in Hirosawa materials. So on the left-hand side, I show the crystalline structure of the Hirosawa materials, which has the manganese atoms to form the ferromagnetic order. And the crystalline structure of this system is a D2D symmetry, which allows the anisotropic Jaroszewski-Mirror interaction. And this anisotropic Jaroszewski-Mirror interaction can stabilize antiskyrmions. And indeed, it was observed in the real space low-density measurement, as shown in the middle panel. So here we can see the formation of the antiskyrmion crystals in a triangular lattice, and it shows a six-fold rotational symmetry. And importantly, the antiskyrmion crystal phase is quite robust in these materials. So appears in a wide range of the parameter regions, even beyond the room temperature. So motivated by the discovery of antiskyrmions in Hirosawa materials, now we consider a simple two-dimensional spin model, which contains a ferromagnetic exchange coupling and anisotropic Jaroszewski-Mirror interaction and a Zeeman term. So here, the anisotropic Jaroszewski-Mirror interaction consists of the inverted sign of the Jaroszewski-Mirror interaction along X and Y axis. And this is allowed by the crystalline symmetries of the D2D systems. And this simple Hamiltonian can reproduce the magnetic phase diagram of the Hirosawa compound, stabilizing the helical phase, antiskyrmion crystal phase, and the ferromagnetic phase as a function of the magnetic field. So on the right-hand side, I show the spin textures of the antiskyrmion crystals obtained by Monte Carlo annealing method. And here, this green dotted square indicates the magnetic unit cell of these antiskyrmion crystals, which contains two antiskyrmions inside. And performing the Holstein Paramarkov transformation, we can obtain the magnum band structures of antiskyrmion crystals. So there are three important symmetries in these systems, and they are C2 rotation about x-axis combined with time reversals, and also C2 rotation about y-axis with time reversal, and finally C2Z rotation from the center of the unit cell. And we can see that these symmetry operation of C2Y combined with time reversal indeed restores these spin textures of antiskyrmions. And the important point is that this symmetry gives constraint on the topological invariance of higher order topological insulators. In this case, it's a Magnonic quadrupole moment, and they can take only 0 or 1/2. So computing the magnum band structures from the magnetic cell, we obtain the magnum band structures as shown here. And we found that these lowest four bulk states, which is highlighted by the magenta color, actually carries a non-trivial Magnonic quadrupole moment. And so as a result of the bulk boundary correspondence, we expect Magnonic corner states to appear in this bulk band gap highlighted by the yellow color. So now we turn our attention to finite systems. Here I show a spin textures stabilized at various magnetic field, and from the high magnetic field level at C, initially we have a twisted magnetization along the sample boundaries. So antiskyrmions are repelled from edges, and they are only found inside the bulk of the sample. But as we decrease the magnetic field, we see these fractional antiskyrmions to be stabilized along the sample edges. So they are cut into half at the sample boundaries, and so carries a net fractional topological charge. That's why we call them fractional antiskyrmions. And further decreasing the field, we see they are become more and more stable and appears at all edges, along all edges of the sample. And the important point is that these fractional antiskyrmions play an important role to stabilize Magnonic corner states. So here I compare two different samples and their Magnon spectrum. On the top panel, I compute a Magnon spectrum for example, with fractional antiskyrmions. And we find 4 degenerate in-gap states within this bulk band gap, and they are strongly localized at corners. So they are indeed Magnonic corner states protected by that non-trivial bulk quadrupole moment. However, just by increasing the field and so that fractional antiskyrmion no longer stable in the lower sample, the corresponding spectrum shows no in-gap states anymore, but instead we find that they are indeed buried among the bulk states. And computing the wave functions, we also find that their wave functions no longer localized at corners because of the hybridization with bulk states. So the reason why Magnonic corner states are not found in this lower sample is due to the symmetry breaking of the spin textures in a finite system. We can actually see this just by looking at this antiskyrmion in the middle columns slightly displaced vertically from the center of the magnetic inner cell. And in contrast, the repulsion between fractional antiskyrmions and antiskyrmion in the bulk restores the nice symmetric magnetic inner cells even in a finite sample. And this is why we have a symmetry protected Magnonic corner states, as we show here. Finally, I'd like to comment on the experimental observation of Magnonic corner states. So firstly, Magnonic corner states can be excited by sparsely uniform AC magnetic field. So here I show the spin wave resonance excitations of a finite sample, and there are 2 large peaks coming from the bulk excitations of gyrotropic motions and the breathing mode of skyrmions. And there's also additional peak from higher energy bulk excitation. So there are 3 well-known magnetically active excitations, but in addition, there's also another peak that is obtained only for finite sample, and they correspond to Magnonic corner states. So just by applying the AC magnetic field at these resonance frequencies, we find a strongly localized spin wave excitations at corners. So we can excite Magnonic corner states by in plane or out of plane AC magnetic field at low frequencies, and they could be detected by ferromagnetic resonance technique or other techniques such as NBA center magnetometries or near field real-light scaffolding techniques and so on. But another important problem is we need to stabilize fractional antiskyrmions to realize Magnonic corner states. And recently, we were able to observe these fractional antiskyrmions in Hirosawa materials. So here, near the sample edges, we can see a triangular shaped object, and they are cut into half of the sample boundaries. And indeed, they correspond to fractional antiskyrmions, which were stabilized at low magnetic field in the Hirosawa compound. So this experiment suggests that the Hirosawa material is an ideal platform to search for Magnonic corner states, but we should also note that Magnonic corner states can be realized in conventional skyrmion crystals, as long as we can stabilize fractional skyrmions. So I'm also looking forward for further studies on these fractional skyrmions in chiral magnetic systems. So in summary, I have shown that antiskyrmion crystals host Magnonic or topological insulators characterized by Magnonic corner states. And for the realization, we need fractional antiskyrmions along the sample boundaries, and they can be realized as we decrease the magnetic field. So thank you very much for your attention.